drill. Differentiate 4x cubed. Quickly, answer. 12x squared. Yeah. What's the first differential of e to the x? Differentiate e to the x. Table of standard differentials you'll need. And integrals. What? That's just e to the x, yeah? That's why the number e is special. Because the differential of e to the power of x is itself. Yeah. What's the value of 3x squared when x is 3? Yeah, that's 3 times 3 is 9 times 3 is 27. Yeah? What does that mean? 10 with an exclamation mark. Factorial. Yeah, that's 10 factorial. What does 10 factorial mean? Yeah. Victorian? Oh well. 10 factorial means yeah. And what happens in the power is you end up with 1 times 2, 3 times 4, and then that's easier. Alright. And you what are the conditions for function to diverge? So what does the term diverge mean? Yeah, diverge is that the numbers are getting further apart, so they're getting bigger, and converge is getting smaller. So what I mean, that's really what it means, but what are the conditions for it? Not sure I can remember myself. Silly. Yeah, I will. What is -1? What is the result of -1 to the power 3? Yeah. Now do -1 to the power 3 without the brackets on your calculator. Without the brackets. Ah, hang on. I do -1 squared without the brackets. And that's wrong, isn't it? Because -1 times -1 is +1. Yeah? What your calculator is doing is just following slavishly the orders of precedence, and that's doing the square first and then multiplying by -1 after and giving you an incorrect answer. Moral of the story, if you're going to power a negative number, put the negative number in bracket. You'll always get the right answer. Because it works okay if the index is odd, but if the index is even, you get the wrong answer. Okay? Yeah? Don't worry too much about divergent and convergent. Okay. Taylor and Maclaurin series. What they are ways of writing power series. For example, power series quadratic 3x squared has got a squared term, an x term, and a constant. Cubic, cube term, squared term, x term, constant. Any one okay, in these power series, there's usually going to be one of each of the powers. So if a function can be written as a power series, you can write it in the form of that function is equal to a constant term plus an x term plus an x squared term plus a cube term, and you can carry on to the nth term. All right? And so on. Now, function must exist condition. Right? So one of the conditions for being able to express a function as a power series is the function must exist at the point of interest. And what I mean by the point of interest will become more clear as we do some examples. Okay? But you couldn't, for this function on here, y is a natural log of x, you couldn't do a Maclaurin or Taylor series around the value of x is equal to 0 because the function doesn't exist there. If you do natural log of 0, you end up with an error, I believe, on your calculator. Yeah? Function does not exist. So, what that means, we could only do power series on this function at the point where x is equal to 0, and soon what that means is you couldn't do the Maclaurin series on it, you'd have to do Taylor series, because Maclaurin series is always centered around the point where x is equal to 0. Alright? So, if we consider the function a point where we write the function as follows. The function is equal to the constant term, okay, point A where it exists, so the A is the point of focus I've been talking about. C1 times x minus A is an x term, then there's an x squared term, a cube term, nth term, and so on. Okay? We would need to find the values of the constants C1, C2, etc. This Maclaurin and Taylor series is about determining what those constants are. All right? Further conditions of defining the function as a power series is that the terms in the series must converge. It means each term must be smaller than the previous one. Are convergent. All right? If the power series exists, we must be able to find the nth derivative. So trying to find these constants mean we have to keep differentiating the function, and we need to be able to find the nth derivative. So we need to be able to find the first derivative, second, third, fourth, fifth, up to however many terms that we want to be able to write a power series for. Okay? All happy with that? And it will become much clearer when we do examples. Starting with the general power series function from the previous page. So we've got now if we let I equals x, what happens to that? CO plus C1, yeah, plus C2 oh, hang on, I need to write a bit more in there. C1 times 0, because that bit is 0, plus C2 times 0, plus C3 times 0, Cn times 0. If I let x equal a, can you see that all the terms except CO are equal to 0? They disappear. Yeah? So, having done that, therefore, C0 equals a function of x. Now we differentiate. F of x. So we find f dash. So looking at our original function, if we differentiate that constant, what happens to it? Disappears. Yeah. What happens here? We've got an x to the 1 term, so we end up with C1. Yeah, constant. Differentiate this term. 2 comes down and becomes a multiplier. Yeah, 1 off the index. So we end up with a 2C2 x minus a plus, and it carries on, 3C3 x minus a squared, and so on. Yeah. Everybody see where that comes from. We then let I equal x again. f dash x c1 plus 0 times 2c2 plus 0 times 3c3 and so on. Everything bar the c1 constant disappears. Yeah. All following f double dash of x. So differentiate this function. C1 goes we get 2c2 what? Where C what are you doing? Yes. Hang on. I want to do plus that 2 comes down, I want to do 2 times 3 C3 x minus a plus that'd be 3 times 4 C4 x minus a and so on. Yeah. What I'm trying to show here is that there's a pattern arises. Yeah, because then when we let I equal x again, and because I is equal to x, all of these terms disappear. So we end up with second differential of x equaling 2c2. Therefore, c2 is equal to f double dash x over 2. Right? Now, in my notes, where's C1? F. I'm going to put in here C1 is equal to f dash of x over 1 factorial. Yeah? And here, C2 is equal to f double dash of x over 2 factorial. That's still 2, because 1 times 2, and so on. Okay? If we differentiate again, it's the last time, pattern will be clear then. The reason for that is that will be the 2 times 1 that we had previously. So you write it as 2 factorial. Right. Third differential So we're differentiating this one. Constant 2 times C2 will disappear. We'll have yeah, 2. I'm going to still write it as 2 times 3, C3, plus 2 times 3 times 4, C4, x minus a, plus and that'll be 2 times. I'll only go up to the 4th one, but you can carry them on. Yeah? And then again, if we let I equal x, all those terms disappear. And f triple dash x is equal to 3 times 2 times C3 yep. Therefore, C3 is equal to f triple dash x over 3 times 2 times 1 equals f triple dash over 3 factorial. Can you see now that if we carried on, you see there's a pattern to this on the end here, in that we continue on to the nth term. Yeah, we know that the constant is equal to the nth differential of that function divided by n factorial. Yeah. Which, oh, hang on, what this, all that means is the value of the differential at whatever x is. It's not the function x, it's not the differential times the value of that differential at the current value of x. So, substituting constants into the original function, we get f at a particular value of x is equal to c1, which is f at a, what we had in it, plus oh, hang on, I missed a bit. Sorry, I've got to have. Done well to fit all that on the board, didn't I? Right. Where will be used. Alright. If we, that's the full pattern, right, for our power series. If we move on to the next slide, what we can do is as, and this symbol here means the sum of all with n being between 0 and infinity. So the infinite series can be estimated as, well, this power series is f to the n, so the sum of all f to the n, x minus a to the n over n factorial. And that's a succinct way of writing what's called Taylor series. Yeah. So we can spread that out to that for the first three terms. Yeah. So here we got the term where n is equal to 0. That's the term where n is equal to 1. That's the term where n is equal to 2. And that's the term of that when n is equal to 3. And we could carry on that for an infinite value of f if we wanted to. All right. Furthermore, if the function exists at the value x is equal to 0, which a sine function does, cosine function does, as you said earlier, ln of x doesn't exist at 0, but if it does exist at 0, we can simplify that power series to here. So the x minus a bit disappears, all right, and you got a much more simplified with, because it exists at 0, we've got what's called the Maclaurin series. So in that term, we couldn't use the Maclaurin series for the natural log of x because it doesn't exist at 0. All right? You'd have to use the more complex Taylor series on a natural log. All right? So what we're going to do now is look at an example. We're going to look at an example of a function that we know what result we get. Yeah, the e to the x, does that exist where x is equal to 0? Do e to the power of 0, does that exist? Yeah. able to use Maclaurin series on that. Yeah. But if you put a value of x is equal to 0 in a function on your calculator, and you get an error, doesn't equal to 0, therefore you can't use it. Yeah. Yeah. All right. So if you've got a function there, okay. Hey, listen, guys. If you've got a function there, and you put the value of 0, x is equal to 0 in that function, and you get an error, you can't use a Maclaurin series, you've got to use a Taylor series. I would think in an exam question, I'll be pointing you to either the Maclaurin or Taylor series. Yeah, I will do. All right? Okay, so what we're going to do is find the first 4 terms of the power series, the function y is equal to cos x. We're going to do it up to the x to the power 6 term. All right? I'm going to do the Maclaurin series. So this is... Right, we've got f of x is equal to cos x. That's what our function is. Yeah? We're going to be building a little bit of a table here. Now, we're interested, point of interest, x is equal to 0, right? So what we want over here is the value of that function when x is 0. What's the cos of 0? Yeah? Our first constant is equal to 1. So if we differentiate, what do we get? F dash at 0 is equal to, so 0. C2 is 0. So there will be no extra in our power series. And that's single dash. That should be double dash. F double dash is, so if we differentiate minus the sign of x, what do we get? Yeah, that's why I'm getting to. You'll with most of these, you'll eventually see a pattern, and you don't need to do any more. Yeah. Okay. So that becomes minus cos of x, and therefore f double dash, because it's minus, you'd treat that as having a constant there of minus 1. So when you differentiate sine x, you get cos x multiplied by minus 1. Yeah? So if you look at this table on derivatives, and you look at sine, you go from sine to cos without changing the plus or minus. But because that's a minus sign, that's going to be minus the result. Yeah? Okay? So the answer to that is minus 1. C3 is minus 1. F triple dash is equal to, differentiate minus cos x, you get sine x. Therefore, f triple dash at 0 is equal to nothing. C4 is equal to nothing. Alright? And now you can see there's a pattern to this in that f, the fourth differential at 0 will be equal to 1. C5 is 1. And f5 at 0 will be equal to 0. The sixth term. Zero. And f vi 0 is equal to minus 1. The seventh constant is minus 1. Yep. Now what we do is we use these constants to put into the power series or the Maclaurin series. Yep. We out the cosine function I'm going to put approximates to, because unless you do an infinite number of terms, it's not exactly equal to. Alright? We've got first constant is 1. The x term, the constant is 0. Putting them in for now, even though they're 0. Yeah. We've got the x squared term over 2 factorial, and the constant for that is minus 1. Yeah. We've got the x cubed term, that would be over 3 factorial, and the constant is 0. The x to the 4 term over 4 factorial, that should be equal to 1. Minus 1, 0, 1 plus x to the 5 over 5 factorial times 0 plus x to the 6 over 6 factorial times minus 1. Yep. That term can go because it's multiplied by 0. That term can go because it's multiplied by 0. And that term can go because it's multiplied by 0. So we can say cos of x is approximately equal to this power series. 1 plus minus x squared over 2 factorial plus x to the 4 over 4 factorial plus x to the 6, that's minus x to the 6 over 6 factorial. And we could carry that on. So for the cosine, we only got powers. Why? Because this one is minus 1 times that, so add negative. Yeah? All the constants are 1, so you don't normally write a constant for 1, do you? But I put them in there so you can see where they come from. Yeah? And you can see that these ones disappear because they're multiplied by 0. Yeah? Alright? So once you've got the constants, you just plug them in to the Maclaurin series formula. Yeah. All right. Now, this is where, while you just finish off getting that down, if we look at that now, after adding, putting in the constant at the beginning, the 1, and the squared term, that's how close a fit we get to the cosine function. If I now add in the next term, so that's x to the power of 4 over 4 factorial, comes in again, yeah, and then it was minus x to the power of 6 over 6 factorial. As we add terms, you get closer and closer to the actual function. Yeah. So the next term would be, gentlemen, plus or minus? Plus x to the power of 8 over 8 factorial. And you're almost over a whole iteration of the cosine wave from there, from minus pi to pi, you're almost bang on. You're not far out even at that point there. Yeah. So although we can quite happily carry out calculus on the cosine function, it does demonstrate that if you can, with a more complex function, you might not be able to integrate, differentiate. You could estimate to the Maclaurin series. But our Maclaurin series, you can see how the estimate centers around x is equal to 0. It's going positive and negative around the 0 point. Yeah. And so we're not very close. Once we get beyond here, we're not very close anymore. But we can get closer if we added more. But we'll never bend back down here very accurately again on that function. All right? So in your notes, you've got the next problem is to find the first 5 non-zero terms for the function f of x is equal to sine x. So create a table like you did for the cosine one. Find what the function is, finding its differential and what its value is when x is equal to 0. We're going to center it around x is equal to 0 again because we're doing the Maclaurin series. Find the power series, first 5 non-zero terms.